So what we're going to talk now is about when your laptop is not enough for your analysis. You need more power. You need some specific hardware in order to perform your analysis. So in order to do that, we are going to present you some, it's not a course that will make you experts in HPC, but give you the opportunities that are available for you to learn. So from this page, I have linked, I'll show you some links later if you want to learn more. And also we have the people from the GPU team from the NRIS consortium who will talk afterwards, who are also working on the LUMI supercomputer. So if you have specific questions or if you want specific needs and you want to learn more, you should, there's much to be done. So this is just an introduction on the things that are available. How many of you here are familiar with HPC or have used HPC? If you raise the hand and give me some indication. Yeah, I see a few. So this one is the presentation I'm going to make a very basic, which is more like a first introduction to what's available. So usually what we do, as the first thing is we run things on our computer. So these days it's most probably the laptops that you use, because laptops has become quite powerful as well. In this laptop you have a keyboard to enter the details you want. Or a hard drive where the analysis, the data is placed in, or the internet, you connect to the network and download something. And then you have some hardware on the machine itself that will help you to perform your analysis. So one specific thing that concerning this analysis, how much work that could be done, is the central processing unit. So this central processing unit is supported by the memory, keep the variables, perform the analysis, have the compiled code to be at disposal at runtime. After the analysis, you would place your data maybe in a display. In the monitor, you might see some image, or maybe it's saved as a file. Then you could share it with other people who would use for other analysis. So this setup we have here is very basic. So in addition to what we have shown here in the central processing unit, there are specific hardware that are optimized for certain tasks. For example, the accelerators or the GPUs that we're going to talk about today could help you to sort of extend the capabilities of the CPU. Or if you are very deep into it, there might be something called FPGAs, programmable feed arrays, that are made specifically for that task. After we learn about that, so later the next the presenters would give you more detail on specifics. So the one specific unit that could handle very specific loads, not all the analysis, is the GPU that we'll talk about in this introduction. Let's have a bit of a closer look at what this could help us with. So here you see some this extremely simplified version of it. So this is not the practical way we do things, might be differ a lot. So in the first part of the diagram, you have one pipe that you could imagine as some sort of pipeline that would do the analysis one by one, and then you have three pipes doing the same thing. So obviously, from the looks of it, if you have more pipes, you could finish the work sooner. But in order to do that, you should be able to break down your bigger problem into manageable, smaller chunks that could be analyzed independently. Not to break the problem totally into separate units, but manageable chunks that could be analyzed separately, and you could combine the results later. So, for example, if these balls were connected, if these pairs were connected with a chain, for example, if you must send one by one, then you can't send them through multiple pipelines. So you have to break down. So when you come to HPC, the first thing that you would need to do is to be able to understand your problem so you could break down. So if you take a specific example, we are talking about something that need 2,400 iterations. So in the morning, Filippo explained something about, during his tutorial, batch mode, doing so many things at a time. Imagine that you have to do 2,400 iterations, one iteration takes 1 hour, which means that if you do it one by one, it will take 100 days. So obviously, if you do more things, more chunks at a time, it will take less time. For example, if you can do 100 at a time, you could finish in 1 day. So if you think about these large language models or large models that has a lot of parameters, they might not even finish in our lifetime if you do one by one. So you have to do it in batch mode. So in order to do this in batch mode, you need to understanding of that concept of central processing unit, some unit that do the processing. Normal, our laptops, they have about 8 cores in our laptop. The processor we have, it also do other things, so not all the 8 cores are available for your analysis. So maybe 5 or 6 things you could do at the same time. And if you think about the servers that are centrally placed in your university, they might be able to do maybe 60, 64 things at a time. And then we talk about accelerators for specific loads. So accelerators are very good at doing so many things at the same time, but they are smaller loads with a specific intention. So the AMD NVIDIA A100 would have 6,900 streaming cores. And if you think of the AMD MI250X accelerator, you have 14,000. And then you have these things connected together. So we have this bedsheet supercomputer with some GPUs. If you take all the cores together, you are talking about 172,000 cores that at your disposal, but there are specific ways to use it. So the LUMI-G supercomputer would have more cores and more GPUs. So the take-off message is, in order to use these machines, you should be able to break down your problem and to make it work on specific hardware. So this is how a machine look like. For example, if you use cloud, if you are running your code on Google Colab, for example, so there will be a machine like this somewhere far away. You connect through the internet and you use it for a while. And we have the HPC system. Let me see whether I have a... Yeah, so it will look like this. So there are no keyboards or mouse or like monitors are connected. All the computers are connected with the network, very powerful network. They reside on the same room. So they could be connected with very fast network connection. And all the computers are connected to each other. All the computers, they have identical hardware. And they have a synchronized clock, which means that if your program could run as if it was a single unit. And they also have access to the shared storage, which means if you place one file in one of these computers, it will be at disposal for all the other computers. So it's your code that would make it work as a single unit. In this link that I linked from the course page, you could read more about these things, more about what these things are, what are the world's most powerful computers compared to cloud, etc. Then working on a HPC system comes with some paradigm shifts compared to what you do on your local machines. One thing is you should know Unix. So without Unix, you could, of course, use HPC. You know, we have Jupyter notebooks connected to HPC and so many interfaces. But if you really want to go into customizing things, do your own things rather than following something already built, you should learn some Unix. So Unix understanding is a basic requirement, I would say, but some might argue against. But I would recommend to learn some Unix anyway if you have time. And the other thing is you are connected to a computer which is on the other side of the network, which means you will type things on your laptop or the computer screen in front of you, but that will actually be executed somewhere else in the network. So you should have that in mind. So some things, for example, a file in your local computer might not be available on the server. Although you see the terminal on the same laptop as you, you're actually on a different computer. So you have to keep in mind when you're working on that. And also we are talking about a protocol. You'll be tool use or a tool, you could say, something called SSH, secure connection, a program to establish this connection. So the SSH is a protocol and a tool. Protocol means a standard way of doing things. So when you type things, the message is taken through over the internet to the other side. So for the sake of the sort of demystifying things, not to show them that they are very difficult or magical things, I will do certain things on the screen as well. So if you can find out whether you have a SSH command by asking the version of it. So if this doesn't report a version or if it reports some error, then you don't have a program that something very basic you need for this, it's not there. And then you have the account. So these resources are centrally located and shared with multiple users. And then in order to use them, you should, as you pay for example, the Google Cloud, for example, when you go, you have some credits. Like that, you have some credits for these resources as well. If you have a grant from Norwegian Research Council, you can get access free of charge, which means you don't pay money, but there are some limitations, how many cycles, how many analyses you could run. So this is the link to get that account. And then what we do is, we will go and establish that connection. So what I'm going to do is, from my laptop, I'm going to go over the internet and connect to a computer in Trondheim called Betsy, SSH. So I have my username. And then I have, I'll connect to Betsy instead today. So here in this material, we have collected all the HPC systems in Norway that researchers can use. So you could connect any of those according to the accounts you have. Betsy, sigma2.no. So there's a specific address on the internet. So this SSH protocol would know where to find it, how to make the connection. So when you type and enter this, you will get a blank line where you enter the password. When you type the password, you will not see any characters on it. So it's just a blank line after the for security reasons, of course. And then you press enter, you will land on that machine. Because I'm demonstrating on this on a wide screen, I don't want to mistake any password issues. So I have made some tricks so I can go inside without a password. So usually it will ask a password. So now, although I see it on my screen, I'm actually working on a computer far away in the internet. And then when you land here, you can use certain Unix commands. For example, print working directory would tell me where am I in. So this cluster partition here I'm showing here. So if you place a file here, or if you install a Python package on this location, that will be available for all the computers. So this is a location where we call it mounted, which means all the compute nodes would have access. So you could install things here and access it from all the computers. But one thing you should keep in mind is that when you make the first connection, when you establish the first connection, you will land on something called a login node, which is a node which is shared by everybody in order to get into the cluster. So you shouldn't do analysis. You should not perform analysis on this. So you're not meant to do that. If you perform analysis on that, it will work as you are analyzing on a server, and it will disturb others, and that's not the way it's been used. You can use it to log in, you could use it to copy files, you could use it to compile things, and to monitor jobs, what's going on. But in order to get the exact power of the HPC, from that login node, you should recruit the cluster, the supercomputer or the collection of clusters, computers in order to do the analysis. For this, you need an additional piece of software, which means we call it a queue manager or a scheduler that I'll introduce in a little moment. So there we do the analysis. Yes, so this we talk about, there are so many parts in it. You could have GPUs as well. And then we have the shared file system I talked about. All these are linked. If you place one file in one location, you can analyze it in others. So in this cluster, I'm going to clear the screen so I'll have more space. There are commands that are listed in the tutorial. You could ask, these are all the nodes that I told you about, 172,000 cores that are available on Betsy. You can use this command to list what things are there. So you see there are a lot of nodes or computers. You could make them work as a single unit. So there are so many people who are using it at the moment. You know how much memory, how much resources are there. So there are people who are using 128 cores at the moment on some of those machines. Yes. Then another issue or something that you should be considerate when you're using in a parallel file system is not everybody would have the same software requirements. Someone might need certain version of PyTorch, certain version of compiler, certain version of Python. Another person might have a slightly different version. There might be some pipelines that depends on a certain version of NumPy. If you upgrade the NumPy, some pipelines would stop working. For this, we need some kind of a magical way of having a lot of software, but not loaded. So for that, we use something called module system. I will demonstrate that with Python here. Clear the screen again to get more space. I will ask Python version. So I have a Python 2 here installed as well. Let's see Python 3. I could ask where it is loading from, which Python. So here. So this Python is loaded here, version 3.68. What if somebody else needs 3.10? So for that, we have module system. I could ask the system, what are the other Python 3 versions available on this computer for me? So there are so many versions. Let's say I want the latest installed. I will load that version. I'll copy paste here so I'll not make any typos. I load that version here. Then if I ask Python version, it will show that version that I loaded. So these modules, it will not only load the Python itself, but it will also load all the other necessary modules that needed for this, without you having to do anything explicitly. You would see that this SQLite is there, binutils is there, a specific compiler which is used. Not some Python modules, they use a C code. If you run on NumPy, there's C code behind this. So this C code need to be compiled, and it is compiled against a certain GCC version, and it also need things like TCL and also maybe libFFI, which means the foreign language. If you want to load some other languages from Python, you need those things. So all these things are loaded. So again, if you want to clear this, I'll ask which Python, again to see which Python is loaded. You see that this is not that earlier Python that I showed you. Then it's easier to clear this. You don't have to log out or anything. Module purge would return the system, sorry, wrong spelling. Module purge would return the system into original level. And if you ask which Python is loaded, Python 3 version, it'll come back. So you can move between versions. And multiple users at the same time on the same computer can run multiple Python versions. So that's why this module system is installed. Is there any questions regarding this? Any comments? Yes.
Can I ask, so where do these modules come from? Are they loaded by the system engineer at the beginning, or is it something that we can configure, for example?
So if I print, there are a lot of modules installed. If I type without any split, it's going to be hundreds of modules installed already. But if you have some specific thing that's not there, you should send a request to be installed centrally, or you could also install this on your home directory. On that cluster location, if you install that location, it will be available as if this software for all the login nodes for your user.
Yes, thank you.
There are more details here. If you want to go deep into and read about this environmental module system and to how to load and how to find compatible modules. Because if you need multiple things, you might need maybe analysis need Python, PyTorch, TorchVision, and TensorFlow together. How would you load together? You can use multiple modules at the same time. The next thing we face is the scheduler. So the scheduler is like when you have shared resources. This one refer to an example as the HPC system. That if there are a popular restaurant, you will see queues outside because the number of people who want to dine and the number of tables might not match. There are less tables. And you might have to make a reservation, before you go into the restaurant. So the person in blue here would be referred to as a queue manager in our HPC system. So we have a software, not a person, managing who do what when. A software, I would say, make a better decision than a human. Then the friends will not get priority. Everybody will be evaluated with the same criteria. And then in the compute environment, you will see words like busy nodes. A busy node is a chair somebody sitting. It's already occupied. You can't use it. Idle means, people could go and analyze there. And then you will have reservations. For example, if you have a course, or maybe one example is during the COVID pandemic, the Norwegian health authorities asked, we want to reserve your cluster to do some analysis, to some statistics to predict how the COVID, the progression would be. So then we had reserved some nodes for them, so only they can come. So when they come to the door, can just go in and sit and dine. And you will also have down, means like broken nodes, which are drained, things like names like that. And the thing you have to take care, make sure that you do is that you don't directly execute on the computer as if it was your own computer. You have to always negotiate with queue manager. So you should be able to pack all the analysis that you need in a file, and you give to the queue manager, and the queue manager decides where you sit, where you do the analysis. That we'll see it as an example in the next step. So we'll run we'll call this a job, this analysis that we do as an example. So this is Unix. I'll create a folder called for this course. So I can easily locate this. So this is why I said we need some Unix knowledge. Create a folder, change the directory, and I'm going to create a file. So here we need a text editor. Here, if you could see that they are using Nano. I'm going to use Vim or Emacs or something here because it's easier for me to type. You can't create your file in, Excel or Microsoft Word or copy to this because there are so many artifacts. You need to find an editor that what you see and what the computer sees is exactly the same. Pure text. No bold text, no underlining, nothing like that. So that's why it's better that if you type on the computer itself using a text editor. So in this one, the first thing I'm going to say is that what kind of language this is in. We call this the shebang. bin bash. So I'm going to write this program in bash language. Then I'm going to issue a command called echo. This script is running on a command, another command. I will save that and exit. Let's see what that file is. So this is the file. Let's see what it does. Do you have a typo, Magnar? Host name, okay. Let's keep that and I'll fix it in a moment. Remind me if I don't. So this one will print some text. Echo is something that print on the screen. And without a dash n, it will print a new line as well, right? And correctly, Magnar point out, I misspell it. I'll just copy the misspelling as it is. So this is also some very important debugging information. When you do on HPC systems or on Unix, you should read what the output is. So here the command did not execute. It says command not found, which means there's something wrong. So if I had typed it correctly, it would have printed as this. So I'll go and fix that. Host. So we have this file. So in the Unix system, you can tell it's a bash command and run it, or you could make it executable, chmod. I would say that it's an executable file, which I'm telling the system it is safe to run. I know that this is something that you should execute, and I would execute that. So I'm going to execute on the login node. In the beginning of the presentation, I said, don't do things on the login node. So I'm going to do something which is very small because to demonstrate that, to show you the difference between the scheduler and execute it directly. It says that it's running on the login node. So now our task is that this is how we directly do it. What are the different things that we need to do when we negotiate with the scheduler? So how would we run this on the compute node is the next step. Let's see how the tutorial says. So here it's directly. And in order to run this, I said we have to pay for this, not in like currency, but in some credits that you get. For this, you need to find your bank account. Projects. This will print the projects that you have access to. When you send an application, you will get a project. You will be attached to a project. So if you are going to apply a project and then going to repeat this tutorial, you have to make sure to replace the examples I use with one of your project that you have access to. You would not have access to the projects I have. Okay, and then I have to send this to the scheduler. So the way I tell the scheduler to execute is that when I execute it directly, I did this. This is same as double-clicking on some file. Just start running it. But for the scheduler, I should say, use the program called sbatch. That means I'm summoning the scheduler. I want this executed on compute nodes. For that, I need to specify how am I paying. Account equals, I will use one of my accounts, NN9970. I hope I have enough credits there. 2 nines. And then I need to, on the Betsy supercomputer, we need to have some specific commands as well, because on Betsy computer, you need at least 4 nodes in order to run that. But otherwise, you could say that I just a pre-processing. I'm just going to test something. The way you tell the computer is with QoS pre-proc, because this uses so much small amount of memory, so amount of resources that you have to tell the computer explicitly that this is just a test. Then you have to mention how much memory you need. which is a very tricky thing because you might know at the beginning how much memory you need. So when your analyzing starts, you might have to do some tests and figure out how much memory you need. Then I have to tell that how much I'm going to stay in the computer. This one, it's 1 minute is enough. Okay, so there's error here. I'll come to that. So 1 minute is enough. Like the restaurant, that when you go into the restaurant, you have to reserve for 1 hour, 2 hours. The reason is because there are so many people waiting in the queue that the restaurant manager or that queue manager should have some idea of how long this person is going to stay. Okay, let's read the message again here. Invalid account partition combination specified. The reason, so if I make it bigger, that I would see that I didn't type my account name properly. So I have a K here, and I missed that K. Then it will submit the job, and it will give you a job ID. And if there's something wrong, something happened, like it didn't perform, it didn't give the correct, not the correct output. If there's an error, for example, if you want to contact the user support, you should accompany this job ID. So that way it will give you so much details about it without you mentioning it. So after the job is run, I will ask the command ls, to list the files. Then I see that there's a file created here called slurm dash, a log file. Let's see what's in it. This process is running on pre-proc. So if you remember earlier, it says login node. So now this is running on a node which is for pre-processing. So the queue manager took this file and found the correct location to place it. Because I said pre-processing, I placed in a pre-processing location, and it ran. So it monitors when it finished, it ended the job, and it gave me back the results I wanted. So this is as if it was you are running directly, but you have to do some negotiation with the queue manager. If you are doing the same thing over and over again, it might be easier that all these things are written into some file instead. So for that, so instead of typing it in the terminal, I could send them into the right in the file itself. I'll do echo. Then I could edit that file. So everything that you need to tell Slurm before about the accounts and about the pre-processing, about the memory and all, it should come before the payload, which means before you do the analysis, you should have that on the top of the file. And the way we tell Slurm that this is something you should do is with sbatch account. So usually in Unix, a hash is a comment. That means ignore this. This is just for my knowledge. But if you type hash sbatch, the Slurm queue manager will read it as an instruction for the queue manager itself, and it will use that information. So I will use the sbatch. So all the commands here should have the sbatch on it. So I don't. Yes, I'm back. Sbatch. I should have just copied that first command. So everything you need to mention to Slurm, you should have it as sbatch here. Then you could run the file. let's see whether there are any errors. S-batch. Then you don't have to mention all those accounts and everything. You can just run the file. Any typos? Oh no, it's just submitted. So that is how you have a file that you want to use for multiple times. So you don't have to mention those things in the terminal. And then, we can move to the arguments of the job script. And let's see how we use a software in our job script that we want to run. So it's not host name that you're going to print always. So let's say if you need Python, some Python version, then you should need to modify this. So I will remove these lines. And I have to clean all the modules and load this specific Python version. So if I don't load this, is there any idea what Python version it would be used? Any comments? So if I don't load this in the job script, it might load the system default Python. So this is a module to print, a job script to print the Python version. And I will remove the log file so it's easier for me to check what it's printing now. So I'll submit that job. Let's. As you can see, the Python version I loaded is the Python version it's using. Any questions or comments? Any clarifications that you need?
Yes, a question.
Go to the question and Little louder, please.
Okay, it works. You talked about Linux and Unix. Do you have a special preference of what type?
You mean the shell like Bash or any other shell?
I would think about like BSD or Linux or Ubuntu or what.
So your operating system, it doesn't matter at all. The Bash has different versions. So you could have TCL, you could have C#. Depending on on that preference, the scripting might change a little bit. But the Bash script, it doesn't change much unless you are going to use a loop, for example. But what operating system you are in, Ubuntu, Windows, Mac, it doesn't matter at all. Because only thing you need is SSH command to connect. So after you make the connection, after that your computer is not used. Everything happens in the HPC system. You could also do it from the Windows. It doesn't matter if your computer is Windows, the laptop. So
you can use BSL if you want.
Yes. Yeah. Or a Chromebook, or even so you could connect from a mobile phone if you want. Yes. Yes. So Magnar, when you make jokes, you have to be a little louder, so we can also laugh. Yes. Yes. So I will create this script. Okay. Yeah. Go ahead.
Yeah. I have a quick question. So in my group, we often use Docker image to train our models. And do you have any comment on it?
So on HPC system, we usually use Singularity, but it's some like containers. On HPC system in Norway, there's support for Singularity, and you could also use Singularity containers or convert a Docker container into Singularity and run. The reason not everything is Docker or Singularity there is that those are compiled, optimized for the system, and those are installed. But sometimes it's not possible. For example, LUMI, when they come later on, it's easier to run containers on LUMI for certain tasks. Magnar, maybe you could, or Hicham could mention that later, the reason behind that. Yes. So on these x86 NVIDIA-based computers, it's easier to, not easier, that's common understanding. It's better we compile it, optimize for the underlying hardware. Yes.
Yeah, I'd just like to also add that quite a few of our winter school students are from outside of Norway. So they might need access. How can they get access to these kind of resources? That could be also interesting for them. Yeah, so.
Yes, so in your country, you might have access. All the countries, they have access to these HPC systems. But you are in the European Union. I'm not sure if everybody, but most of the countries, they have some agreement with LUMI. So you could use LUMI, the example that comes after this. So in order to understand the payload that my colleague is going to explain a little later, I'm going to run a small command to sort of locate GPUs as well. So this is a Python script that I'm going to run to show you that to show you some real scenario, because not all the time you would load modules, not all the time you would print host names and just print Python version. You just want to perform some real analysis. So for this, I am loading PyTorch. I'm using PyTorch to go and detect the GPUs in the computer. No need to understand this code much, but what you could do, what I want to show is, this will use PyTorch to detect the GPUs. So let's see whether I can run it from my computer. So there might be errors, but we'll see. GPU example Python. Okay, syntax error. Any Python experts? Any Python experts who see what the error is? No experts? Okay, so let's ask it Python 3. This is a syntax error. So the second error is different because the first error was because in Python 3, the syntax different in Python 2 and 3. So when I use Python on the system, it used Python 2. So in the second one, it says no module, no software called Torch. Anyone has a solution for this? What was that? Pip install. Yes, so that is the good point. Thank you. That will solve that. But when you have a system like this in a shared system, we have a slight different approach for that. We look for the PyTorch installed instead. Module avail PyTorch. Then we load the module. So this seems a little older, but that's okay. For the exercise, it should be enough. Load the PyTorch module, and then when you load the PyTorch module, you will see a lot of things are loaded. In addition to PyTorch, you see all the dependencies that are needed, optimized, installed on your computer. So when you do a pip install on your Windows machine, it will pull a binary, which is compiled on another machine. But on a Unix system, it might pull the binaries, it might compile, but it will not take care of all these dependencies. When you do pip install, it might ask for something missing. Install this. Then you go into rabbit hole installing so many things, and you'll hit a wall where you can't do anything without administration privileges. You can't do with root. You can't do a DNF install. You can't do a apt-get. Then you go and search internet. Then the stack overflow would say, install this, install that, uninstall that. Sometimes you have to go there. Before you go to that, you have to check whether it's already there. Then I'll ask the Python to run, and if there are GPUs, it will detect. I have to consider because it's a login node, and it takes a lot of time because this PyTorch, it has a very big binary, it will load into the memory, and you're not supposed to do these things on a login node. I'm not preaching the correct procedures here, but just wait. So it didn't detect any GPUs, which means the login node do not have a GPU. So if you have a code optimized for the GPU, and if you run it on the login node without negotiating with the queue manager, you would think that you are using GPUs, but GPUs would not be used. It will just run on the CPU. So in order to run this, I will modify my example script. So here, I'd run this and maybe place the output in a. So this is not not a very good way on HPC to pipe things out, because there might be race conditions, so many threads trying to run write into files, but just for this demonstration purposes. And I forgot the name of that PyTorch module that I load. So when you load PyTorch, it also load a compatible Python version. If I can see here, Magnar, do you see the Python, which number it is? So you load SciPy. Yeah, number 27. So it makes sure that the compatible Python version is loaded as well, and compatible NumPy versions. So all the set, the complete set is there. Then you don't have to load the I'll remove the Python version here, and you wrote the PyTorch, and I will save and exit, and this is how the file looks like. Right, so I'm going to submit this job without any modification, and let's see how that works. What was the command to submit? sbatch. What do you think now it will happen? You're not supposed to do, but it's supposed to know, but maybe there are some HPC users. What would happen? Any idea? The people who said you're already using HPC. Yeah, what was that?
You can check if it's in the line or if it's not.
Yes. Let's see, that's a good point. SQ, you can ask whether the job is running. It's actually finished, it was too fast, so it actually finished. And let's see, the next time I should show that, that's a very good point. I'll see the files, what are the files? And I have this out file, let's see what in that. It didn't find the GPU still. The reason is that there are additional things that might be needed when you are asking for special hardware. Because we don't want people, if you don't need GPUs, just log in and just wasting the hardware. So there are specific needs. And specifically we need this file. Let's see, I need to say, we could also have this inside the job script itself. We need to say partition. Partition equals accelerated, which means with the GPU, and I need one GPU. GPUs. One, and I think I should remove one instruction from this inside the file. Let's see, because the pre-processing pipeline might not have GPUs. I remove that. And I need a little bit more memory for this. Maybe at least 8 GB to load these PyTorch binaries. Then I will submit that. Then that command, that good point you reminded me, sq -u, what's going on? It means running. So this could be, the status could be running, pending, finished, carrying forward. So I could check that now it's finished. Then it will see the output file. It managed to acquire NVIDIA A100 with the 40 gigabytes of memory. It detected that. So the next step in your PyTorch would be, after the detection, schedule the job, provision the job according to the PyTorch, detect the number of cores. Then you could inform the rest of the libraries how to use it. So that is just a taste of what we could do. And in this tutorial, there are more things. How to customize it. How would you ask how many cores you need. do you need all the cores in one machine or you need in multiple machines? So later on in the next two sessions, you will see the power of distribution, which means that in these powerful computers, there are multiple nodes. The power of analysis come in a way that if you can provision things to happen in multiple machines. So that's a very important thing that you should learn if you could. And there are libraries that will do that for you. So that you will get an idea later on. And here I'm not going to talk more about these things because that's the basic idea of what I want to give. And maybe I'll give some more time for my colleagues to go into the real use cases. So any question? Yes, Hicham.
Is this something that students can use?
No. So the students need to apply for the project. So in the first slide, I have a link how you could get access. So when you type the project, you should be able to, because not all of here are NRIS users. Yeah.
Because the idea is good if they can get access, at least for a short term, then they can run some benchmarks. That's
yeah, for you.
no, for them. Not
Yeah. So then they need an account first. So there are few people who are with accounts. Most of them, they are not with accounts, and some of them are foreign students. Yeah. So they could run it in their HP system if you can share the code with them. Yes. You could come and
Yeah, there's a question.
get ready.
Yeah.
Hicham, you could get ready until they ask the question. Yes.
so this part will somehow will complement what Sabry he was talking about. So at least the first part, but mostly will be about distributed training. But before we start, I would just want to ask if you are already familiar with distributed deep learning. Maybe you can raise your hands to see, just to get an idea how many they are more familiar. Well, we have 1, 2, 3. 4, okay. We have one here, one hand here. Okay. So probably, yeah, there are some familiar with distributed training. That's good. First question. Let's start by the first question. Why distributed training? So, well, basically, there are many reasons why distributed deep training. First of all, you might run on memory limitation, especially when you run large models or large data sets that basically wouldn't fit in a GPU, single GPU memory. And that's, of course, running things on a single GPU memory when it's limited, of course, it limits the batch size and the conversions and the performance. Obviously, they are not accurate enough, which is not good. So that's why you basically, when you have large model, you want to train a large model, or you have large data set, you basically need a large HPC system in order to fit the large system in a large HP system. But more importantly is you want to run it, the run time performance want to be as short as enough and benefiting from the capacity of an HPC system. So just to highlight what I'm talking about, this is an example where it indicates a need of distributed training. So this is in the context of drug discovery, and you can see that the database, basically the size of the database increases the last 10 years, reaching about 40 million molecules. So then you can imagine if you have 40 billion, not million, 40 billion molecules, you can imagine that a single GPU obviously wouldn't fit in this context. And the more accurate example here is in this study, with that's in the context of the corona SARS. So where they train about 40 billion molecule, and that took about, as you can see, So it took about 90 days to run the training over 250 GPUs. That's an example where distributed is really needed. But of course, if you run an application that doesn't require multiple GPUs, of course, you don't need to do distributed training. Another example that in the same context, the same study with it, where the application runs on the entire Summit supercomputer that has about 27,000 GPUs. And that was run in 1 day. So this is an example that indicates really the need of distributed training, if it's needed, basically. And what is needed, of course, is you need a large HPC system in order to do this kind of training. Another survey in the context of training here is some papers where they run some experiments, and you have on the left-hand side, this is the experiment and over the last 10 years. And you can see that the majority of the experiment in the last 10 years, they start using GPUs. So, I mean, you can see that the percentage of using the GPU increases in the last 10 years, which indicates the need of GPUs for machine learning. On the right side, you can see that the difference between the color here, the single node and multiple node, which means running machine learning on multiple nodes. And you can see that there was a need in the last 10 years in using multiple nodes. So this is this is a clear indication that the increase of the data set requires using a really large system, because this offers the possibility of running on multiple nodes, meaning many GPUs. So that's why this presentation will cover basically 3 parts. So the first part, we'll talk a little bit about a compute node in an HPC system, mostly the supercomputer LUMI. So then I will focus a little bit on the concept of different distributed training architecture. Understanding the concept is really very important, especially when you are using a framework, and that helps understanding the framework itself better, and also it prevents you from using a framework by simply modifying parameters without understanding the functionality of that framework. And this is really very important. And in the last part, I will take the example of Horovod integrated into TensorFlow, and we will go through an example, an application together, and we see how we can distribute an application that is based on single GPU to run over multiple GPUs. So what I expect you basically by the end of this presentation you can learn is that you will learn a little bit about the architecture of a compute node in a large system that integrates both in a heterogeneous system that integrates both CPU and GPUs. So you will understand the difference between model parallelism and data parallelism. You will get some understanding of conceptual difference between centralized and decentralized architecture in deep learning, and you will understand or you get some insight into the concept of Horovod, because that's the framework we will be using in the implementation part. And hopefully by the end, if you get an application, you will be able yourself to implement Horovod. So I cannot guarantee that by the end, but I think it's very important that you make an effort on that. And understanding it, of course, it takes time. So that's the learning outcome that we have achieved by the end of this session. Okay, let's start by the supercomputer LUMI. So the LUMI, the partition G, which has GPUs, it consists of about 2,000, almost 3,000 nodes. And it's basically, it's an AMD, it consists of AMD CPUs. Each node has 64 CPU core. And on each node, it has 4 AMD GPUs, I.2-Basics GPUs. But such that each AMD GPUs consists of 2 graphics compute dies sitting together. And the memory with 120 gigabytes of memory per GPU. Per GPU, I mean per AMD I.2-Basics GPU, or 64 per GCD. But we will see another picture where you can see a bit clearer these features. The nodes, compute nodes in LUMI, they are interconnected via slingshot. It's not InfiniBand, it's slingshot. And each GPU node features about 4 200 gigabyte of network interconnect cards. So yeah, the total, so you have a total of 512 giga of memory on each compute node. So if we go a bit to see how the compute node looks like, I try to divide, this is a compute node. The white line divides the GPU part on the left-hand side and the CPU part on the right-hand side. So, and then you can see some interconnect here, which are described here, and the bandwidth associated is also described there. So if we start from the GPU part, the GPU partition here, you can see, so as I mentioned, there are 4 AMD 250X. You have 1 here, 2, 3, 4. Also mentioned that on each AMD GPU, they are sitting 2 GCD. This 2 GCD in the SLARM, Sabry he mentioned in SLARM system, is considered as a singular GPU. So this GPU, with this GPU, they are the bandwidth between these 2 GPU is you have the peak bandwidth here, bidirectional bandwidth is 400 gigabits per second. The interconnect between this GPU and this GPU is 200 gigabits per second. So what that means, it means that if you run your application and you are able to communicate between this GPU and this GPU, it will be twice faster than running on this GPU and communicating with this single GPU. So that's why the understanding on having an overview of the architecture of compute nodes, it helps in terms of optimization. Another thing is that each AMD GPU, there is a network interface cards. So you have for AMD, so you have 4 network interface card. There's an interesting aspect of this network interface card. The example here is GPU direct technology, which is if you want to communicate between a GPU in a node 0 with the GPU in another node 1, without passing by the CPU and then from the CPU to another CPU and then from the CPU to the GPU, which increases the communication overhead. By enabling this GPU direct technology, you directly go from the GPU memory to the network interface card, and directly from the network to another node, and then to the GPU. So this is an optimization option that you could do without really any effort, because simply exporting the environment variable, because the administrator taking care of the system, they take care of the installation of this kind of of technology. So this is about the GPU part. So the CPU part, we have 4 NUMA node here, NUMA 0, 1, 2, and 3. So you can see that on each NUMA node, you have 2 CCD, compute complex die, and each one here, you can see that consists of 8 CPU core with a shared L3 cache memory. And each of these is connected to a specific GPUs. So let's look at a little bit how this CCD looks like. So that's how it looks like. So you can see, as I mentioned, it has 8 CPU core. You have 4 on this side and you have 4 on this side. So each CPU core here has 32 kilobytes of cache memory, and L2 512 kilobytes of L2 cache memory, and all of these CPU cores, they shared L3 memory. And what you can take from this picture also in terms of optimization is that L3 in terms of memory is large. The problem is access in the memory L3 is a bit slow compared to L2, compared to L1. Meaning that if you want to add more optimization, you need to focus on accessing the memory L1 rather than L2, rather than L3. But the worst thing is that if your application systematically is accessing the main memory, and then the latency increases and the performance of your application will be poor. So that's what you can get from this picture. So that's what I mentioned, that understanding the architecture of compute nodes, it helps really in terms of optimization. So any questions here before we go to the, yeah?
So I was curious about the L3 cache, since it's shared between a collection of 8 cores. Are there any problems with contention between cores if they all your cores are reading from this same spot?
No, definitely no, because that's the interesting thing about L3 cache, is that all the CPU cores, they can read and access the same memory, which means it makes the computation really very fast. It reduces the latency, basically. So that's the interesting aspect of it.
Thank you.
Any other questions? Yeah?
This is a dumb question. Why to try and run a game on this?
Sorry, trying what?
Run a game.
Video games.
How many do you have a huge fan party?
Well, basically, I mean, this large system, they are designed for heavy computation, for science. So, I mean, if you want to do gaming, I mean, then you don't need to, because this is with double precision. Gaming, you don't need really such a precision. So it's, yeah. Okay, so this was about the first part about the HPC system. Yeah, this is a very general picture where you can see compute nodes, where you can see the NUMA node that I was talking about here. You have the NUMA node here. This is the GPU memory, and you can see that each CPU core can be connected to a GPU. And this is also an interesting picture because it helps you to bind a specific CPU to a specific GPU and then take benefit of the networking of the architecture. So now we move to talk a little bit about the concept of distributed training. So as I mentioned, we will make a difference between discuss the concept of model parallelism and then data parallelism. And then the next part is we focus on data parallelism and we address both centralized and decentralized training. We start first by this is a single work, a single application when you have a network that runs only on a single worker, a single GPU in our case. Of course, you have the data here that as an input, you do your training. The question here is how this picture, which is sequential, how can be parallelized such that it can run on multiple workers. So that's why we use this parallelism methodology, and basically what parallelism what it means here is just training large model or large data set on multiple work, either on a shared memory or on a distributed environment. When talk about distributed environment, meaning taking benefit on multiple node instead of doing the parallelism only on a single node. So that's basically the concept of parallelism here, what it means. And we distinguish here between two modes. The model parallelism on the right-hand side, and then we have the data parallelism. So the concept of model parallelism is that, as you can see, that the model itself, the target model, is partitioned into multiple parts, such that each part will be assigned to a worker, and that the data remain the same. There is no changes in terms of the data. The data parallelism implies that the target model is partitioned into multiple parts, such that each part will be assigned to a worker, and that's how the model parallelism is done. On the other hand, for the data parallelism, you can see that this picture is replicated over multiple works. So worker 0 has the same. You can see has the same picture. But the particularity here of data parallelism is that the data is partitioned into multiple portions, such that each worker will operate on a different subset of data, but keeping the same target model. So in this way, you simply replicate your application like it runs on a single GPU, but the application here, it operates on a very specific data set. So unlike in the model parallelism, where the data, there is no partition of the data, but only the partition happens at the level of the target model. So the particularity here of the data parallelism is, first of all, it's very simple to implement. Another thing is it offers the possibility of scaling scaling the performance over multiple workers, because each worker, as we said, the application is replicated on multiple workers, and that makes the scalability very optimal. But of course, when you increase the number of workers, of course, the scalability will have some issue, and we will see that. So that's regarding the difference between model parallelism and data parallelism. So now we move to the architecture of centralized and decentralized distributed deep learning. So I guess you are familiar with this equation. That's the neural network gradient. So, and in this case, I try to write it in the way that is the sum here. You have a sum. The sum itself is split over the number of workers. Just to make the picture clear when explaining the concept of centralized distributed centralized distributed learning. So the picture here is that in this picture, what happens is, so you have your data here. The data is partitioned according to the number of workers, as we mentioned, because this is a data parallelism. So, but you have a number of workers, worker 1, worker 2, and so on, and then you have servers. So, so what happens here is the worker, they need to get some weight from the server to compute the gradient or subgradient. That's what I mentioned here, the gradient, because you can think about it that each worker will compute the gradient. Each worker will compute a sum of a gradient. But then you need to aggregate all the sum in order to update the new weight. So the worker will get the weights from the server. They need them then in order to compute the gradient. So now each worker is computing subgradients. In order to get an update of the weight, you need to aggregate all the subgradients and then generate new weight. So that's what happens. So each worker will send their gradient, compute gradient to the server. For instance, the worker 1 compute the gradient 1, the worker 2 compute the gradient 2, and so on and so forth. So now the server, what it is going to do is it will aggregate all this gradient in order to compute the total gradient. By computing the total gradient, it will update the weight and then go back again. Each worker will try to get this weight and do the computation again. So in short, what happened here, in this picture or in this architecture, you have the parameter server that collect all the subgradient and compute the gradient and then update the weight. So, and each worker will pull the weight from the server and send the value back to the server and so on. What you can see here is that there is no interaction between worker 1, worker 2, and so on. All the workers, they will interact with the server. And that's probably one of the inconvenience here, because this will generate communication overhead. And the communication, too much communication, that will be push pressure on the server, that will generate a poor scaling. So the alternative to this approach is decentralized training architecture. So in this case, first of all, you can see there is no there is no servers. You have only workers, worker 0, worker 1, worker 2, and so on. And now in this picture, each worker is going to compute its own subgradient. And then this worker will exchange the value of its gradient with the neighboring one. Because at the end, each worker will compute the subgradient and will get the value, the total value of the gradient. Which means at the end, all the workers, they will have the same value of the gradient. That sounds a bit... So what is important here, what is important here is that all the workers, they will interact with each other. That's one thing. Another thing is they will not have the same weights as in decentralized architecture, because they get the weight, they get the total gradient from the weight from the server, all of them. So here, each worker, they will have their own weights, because each worker, they will operate on a different set of data. So, and this is a picture that basically is implemented in many framework, because it's very optimized, and the algorithm that is done to compute all the gradient in this way is ring all reduced, and we will come back to that later. So as I said, there are many frameworks that implement these concepts. So this is an example of TensorFlow, where we can show the performance when it comes to large-scale training. So here there are two models. And you can see here, this is the image per second. When you go from 1 GPU to 16 GPU, the scaling is okay. But then when you go from the 16 GPU to 128 GPU, you can see that the scaling is really poor. So almost 50% of resources, they are wasted. And this is the same for this model. So in this picture, what you can see, there is a poor scaling because of a poor communication between this communication overhead, basically. Another thing with the TensorFlow, it implements many concepts, which makes it very difficult to debug the application that's based on TensorFlow, distributed TensorFlow. So that's why, in our case, the alternative that we are going to use in the second part, we are going to use Horovod, and I'm going to show you that it's very simple to implement, and it's very suitable for large-scale computation. So I think, I have a quiz for you before we can move to the second part. Okay? So we can just take it very random and see if I'm able to you are able to follow first, and I'm able to explain a little bit in a proper way. So the first one, in a centralized distributed training, there is a direct communication between workers. Is that correct or true or false? Just raise your hand. False. Okay, that's correct. Okay, the second one, in centralized distributed training, each worker gets weights from the server. True. True. Oh, okay, that's correct. And the centralized distributed training, all workers directly communicate with servers. True. That's correct. Okay. So all workers have the same weight. Yes? True. It's true. Yes, that's true. Okay, let's go to the second part. In decentralized distributed training, there is no parameter server. True. Yeah? Okay, that's correct. In each worker computes gradient and exchange its value with other workers. True? Yeah, that's true. That's obvious. Okay, each worker computes its own weight. Yeah, that's true also. Each worker exchanges weights with other workers. Wait. Yeah, that's false. Okay, so I think you are doing well. That's this part is it went really good. Okay, let's move to the next part, which is in this part we'll focus a little bit once again about the concept of Horovod to understand a bit Horovod, and then we go to the implementation and take an example and work on it together. Okay. Yeah. So what is Horovod? So it's an open source library for distributed training on multiple GPUs across multiple nodes. So it's an open library. It provides functions and function wrappers, and it's integrated in TensorFlow, Keras, PyTorch, MXNet, as far as I know. So that's the majority of that's the machine framework where Horovod is integrated in. And Horovod, that's the most important aspect, is that it's based on MPI. So it can be built with NKL, that's NVIDIA collection communication library, and GLUE is a communication library developed by Facebook. So what you can see here that Horovod is basically simply is an MPI-based thing. But the most important about Horovod is really the result of these three works, these three papers. The first paper is by Facebook, where they show that adjusting learning rate, it gives some interesting result. Instead of scaling the batch size, scaling the learning rate, that's one aspect of it. Of course, the first aspect is the data, decentralized data parallelism, and use learning rate, scaling learning rate. This is a part taken from Facebook paper. The second part, which is really the key that makes Horovod very optimal and more suitable for large system, is really the algorithm, optimal bandwidth RIN algorithm developed by this author here. And based on this algorithm, they develop a library that is available. So overall, Horovod is based really on this. Is based on really on these works. And I mean, to understand a little bit much better the concept of Horovod, so we have talked about data parallelism, and I like also to have this equation there. Then we can see the connection between this picture and this the subgradient there. So I'm going to repeat it again, but this is in a different way in the connection of Horovod. So initially, you have each worker basically will read a portion of data that will be fed to the model. So then the gradient will be computed, but once again the gradient of based on the subset of data, and then you need to do the average here. And computing the average is really here where you have to interconnect with all the workers. And once you compute the average, then you can go back again to the model and go in a circle. But the key here is really, in order to update the model, you need to compute the average gradient. You compute the gradient, but you need this one. And in order to compute this one, you need the value from other workers. And this is the algorithm. It doesn't appear clearly. Yeah. Well, what I mean there is this: how the average gradient is computed, and this is the basic concept of a RIN or reduce algorithm that enables to compute the average gradient on all workers. So to understand this, we take the example of we have three workers. Worker A, B, C, and we have some values here that are values of subgradient, okay? So each worker here has its own value of subgradient, and we want to average that. So what would happen in the second step is that the worker A will exchange its value with the worker B and sum up. So you end up with 13, 14. So what happened is 5 plus 8 and 13 plus 11. Then you get 13 plus 24. And the worker B, what is going to do the same? It will exchange this value with the worker C and compute the average. And C will do the same with A. So it will exchange the value of the subgradient with A, and then it will compute the average, which is 55. And you do that over and over, so at the end you end up that all the workers, they contain the same value of the gradient. So that's how the average gradient is computed in Horovod. It's using this RIN or reduce. And the way this algorithm is designed is in this picture is that you can overlap communication, which means you can transfer the data, but at the same time do computation and makes it even more optimal. So let's see how much time we have. This is a picture where it shows how the scaling of an example of a training language model training using Horovod over up to 40 GPUs. So you can see that the scaling here is very linear until 40 GPU. And there's also another experiment here where with the comparison, the red one, this is TensorFlow, and the green, this is with the Horovod. So you can see Horovod scales up to 128. You can see that's almost 90% scaling. But also, I mean, it's also suitable for small scale computation. So it's, but the point here is you see the impact or of Horovod when compared to other already available framework is really when you go very large in number of GPUs. Okay, so let's look at the implementation, how to implement Horovod, and we look at it. This is an implementation in the context of Horovod, using Horovod integrated to TensorFlow. So the first thing, of course, after importing the Horovod, you need to initialize Horovod, and this is simply, if you are familiar with MPI, this is just simply an MPI initialization. So then the second part, so this is basically just TensorFlow. Then you need to list the devices and this allocated the memory. So this is when you assign a visible device to a local rank. So what this picture means is it's mapped here that what you do is each CPU will be connected to a specific GPU. So what does that mean? It means that you cannot assign two ranks to the same GPUs. You can't do that. One of the reasons is that, first of all, is GPUs, they are designed for, they are not designed to handle multiple processes, but rather for multiple threads. So that's why, so this is very important. So each CPU core will be assigned a specific GPU. So the CPU core 0 will be assigned the GPU 0, the CPU core 1 assigned the GPU 1, and so on and so forth. So that's what is done here. It's just assigning each CPU core to a specific GPU. And then the second part, you need to scale the learning rate. So one of the important points to understand here is that when you do the scaling here, you need really to do some warm up, because scaling from the beginning will result into very poor accuracy. So therefore, you need at least the scaling should happen after a warm up of 3 epochs, or basically you need to run some experiment. And the key really here of Horovod is really this point, because what takes time in training is really computing the gradient, and that is really where Horovod comes to play. It's really this part. So basically here you apply the Horovod distributed optimizer to the original one. And everything is under this function, which means this function that computes the gradient. There are 2 ways how to do it. If you are using this syntax, or you can use, or if you are using gradient tape, then you can use this syntax. And and then the other step is you need to broadcast the variable from the root to other ranks, and this should be done after initializing the model and the optimizers. So the last point here is you need the checkpoint needs to be saved on the rank 0 to avoid overwriting the files by other ranks. So this is a general picture. This is a general picture about how to implement Horovod. So now we can take, yes, I put, there's a tutorial here that you can access. And this is, the tutorial is, you can find it in the file example here. And there is a job here, a Slurm job, that you can look and you can, if you have access to LUMI, so that's something that you can run it on LUMI. But of course, you can adapt the job script here to run it on an NVIDIA-based machine. And there is a Python file here that you can run to check if all the libraries they are installed in a proper way, they have a support of Horovod. So if you try to run this benchmark and you are experiencing any issues, that's just write to me and we can look at it together. So we take this simple example, and sorry. So I split this screen in two parts. There is a single GPU tree in here, and there is distributed tree in here. Okay, then we can see the difference, and then you can notice the simplicity of implementing Horovod. So this is training some MSIT data set. So initially, after importing all the necessary packages, so you initialize as we mentioned, and you need to assign each GPU to a specific device, as we mentioned previously. So that's the first step. The second step is when you prepare your data set. So there is a function. We have a function that doesn't need to be changed in terms of in this example for both single and distributed training, and that's for preparing the data. So in this simple example, since there is here only a single GPU, so the default rank will be 0. However, here in this case, each rank will basically access a different set of data. So and that is according to these two arguments, which means rank 0 will access a different data set, rank 1 will access another different data set, and so on and so forth. Because this is a simple example. But if you have probably another scenario, you want to distribute the data across multiple rocks, multiple workers, and in this case, you can use, for instance, char function. And in this case, the size or the number of GPU of workers is assigned to the number of char, and the rank, the index of rank is assigned to the index here. So after preparing the data, you initialize your model the same way as in the single GPU. And then here is the optimizer. You set up the optimizer here. We have our optimizer. So the modification here is just simply scaling the learning rate. That's the only thing is done here. Yeah. So then you wrap the optimizer to the original optimizer to Horovod-distributed optimizer, and then the next step is compiling the model. You compile the model here. So what is the difference here? You can simply add this function. This is a TensorFlow function. It's just a test TensorFlow to it tests TensorFlow that the gradient will be computed by the distributed by Horovod distributed, just to ensure. And here comes so this is we are initializing. So here where you do the broadcasting of the initial variable to ensure consistent initialization of all the worker trainings. So here comes your question. So here where you have to specify the warm-up epoch, for instance, up to 3, to avoid, when scaling the learning rate, to avoid getting bad result. So this is a very important point. And there is more details in the Facebook paper. if you want to get more details about issues when scaling learning rates and different strategies there. So the last point is that simply you save the checkpoints in rank 0, and the rest is the same. So you can see this is a simple implementation that, a simple example that really indicates the simplicity of implementing Horovod. And you have seen the experiment in terms of large-scale computation, where the scaling is just perfect. Any questions so far here? Yeah. So now how to run Horovod. If your system has support of OpenMPI library, you can simply on a single node launch your application with MPI run, and then your application. On multiple nodes, you launch with MPI run, but then you have to define the different nodes. In the case you have 4 nodes, then you have to define these nodes. So now, if the system does not support OpenMPI, I think the simplest is just to launch it with slurm srun command, srun python main, and that does all the job. This is something, the reason why we talk about OpenMPI here, because Horovod by default is built with OpenMPI. But you can build it if you have a cry system, for instance, which is the case of LUMI, you can build it with MPI CHI library, or you can, or it has support of other MPI libraries. And there are any questions how to run? Because also, if you go to the repo, there is also a description of there is a job description there how to run it on LUMI. So then you can get more details there. Any question? Okay, the last thing is that Horovod also comes with for profiling or debugging. It comes with timeline profiling. And very simple it's very simple. Simply you need to export this to enable this environment variable pointed to the name to the file, and this line needs to be added to your job script. That's simply what needs to be done. So once you generate this file, you just use this viewer to view the analysis, and you can get this picture that you can zoom in and zoom out to get more information. I think probably I will just stop here. So in this picture, I want to talk about the binding option, which is the case when if you want specific CPU to run on a specific GPU, you say there is a mask here that you can specify, but this is also valid if you have exclusive GPUs. Otherwise, it wouldn't work. So I think that's my conclusion. So in short, what we have talked about the difference between conceptual difference between model parallelism and data parallelism, and also decentralized and decentralized. So the majority of a framework that scale very well is really make use of decentralized distributed with the RAIN all reduced algorithm. So this is really for me the key aspect of Horovod, which makes it very simple and more suitable for large-scale computation. It's really the ring all-reduced algorithm that makes it very suitable. It comes with Horovod time profiling to profile the application, and it's very simple to profile. It's only profile what Horovod does. When it's integrated to TensorFlow, it doesn't tell you anything about TensorFlow. It tells you only about what Horovod is doing. So, yeah, with that, I thank you for your attention.
Okay, I wanted to remind you that our talks are available from the NLDL webpage. And my slides are here. And I'll also refer to some tutorials when I speak. And you can find them there in case you want to reproduce my work. Anyways, let's get started. So, my name is Magnar Bjørgve. I'm an engineer here at UiT. I'm affiliated with both NRIS and Nike. And I'm going to talk about GPU monitoring on LUMI-G and Jax on LUMI-G. So we'll start with the GPU monitoring. So the tool we use on LUMI-G is the ROCm-SME tool. We mainly use it for monitoring GPUs because we are users of the HPC system. In principle, you can do more, but yeah, we are users. It's similar to NVIDIA's SME that I would assume some of you has heard about before. And it enables real-time monitoring of both GPU computational loads and memory utilization. And it can also be used to determine the topology of the GPU interconnects within the system. This relates closely to what Hicham talked about on the architecture of the nodes and system. And we can use it to answer questions Hicham already answered with the slides, but as a user, you might be interested to see, is this true? And here you can, for instance, get a summary of the NUMA nodes. And if you look closely, you can see that each NUMA node has 2 GPUs. You can also get information on how the GPUs are connected. For AMD GPUs, or at least AMD GPUs we have on LUMI-G, they are connected to XGMI, which is similar to NV4 as the people here that's worked with on clusters with NVIDIA GPUs. And we can also get information like, are they directly connected? And we can see that all of the GPUs are connected with each other through exactly one link. So, something I hope you guys can find a bit useful. Sabry kind of answered it, but a question I always ask myself when I try to run a new application, especially if I'm on a new system and some new kind of tool, it's, am I actually running on the GPU? More often than not, or at least more often that I care to admit, I think I'm running on the GPU, and I'm not. And I can use ROCm-SME to figure this one out. And probably more interesting in the long run is, if I'm running on a GPU, am I utilizing my resources well? So a solution I'm often tempted to go with, if my software is slow, I just try to throw more GPUs at the problem, and it's hopefully faster. But something I've experienced, and I'm sure some of you might have experienced as well, is you're not actually utilizing the resources you are using. And ROCm-SME can be used to figure this out. An example of this is we can use ROCm-SME to show GPU utilization. We have that on the right-hand side there. On this particular application, we're using the GPUs well. We are using 8 GPUs, single node. And we can also see that we're not really utilizing the memory. It might not be needed for this particular application. And a small hedge here is that I did not sample. Both of these are from the same application, but not the same time step. So it might use more resources on the memory at some other points. So how do you do this? Again, if you want to do this yourself, you can find these guides on the training websites. And the first thing we need to know is which nodes are we actually running on. We do that through the sact command. And when we figure out where things are running, we can run the ROCm-SME through srun, which is telling Slurm. Slurm is the server Sabry was talking about. And we can tell Slurm that we want to run ROCm-SME. In this example, we are using show use on top of whatever work is already going on that particular table. But this requires you to actually sit at your computer when you're running the job. What I like to do, I don't like to sit at my computer watching my job run. I don't know, I want to play golf or something. So what I do, I start with my job script. I try to modify it with a GPU monitoring function. Again, if you want to try this yourself, it's available here in the QR code. And in this particular function, I'm telling Slurm to sample my job every 30 seconds and give me the what am I asking for? I'm asking for what's it called? GPU utilization and memory usage. I have it printed to CSV, if you here, and it dumps it all in a file with sampling every 30 seconds. Why CSV? Because I grew up with pandas, and so I'm used to analyzing CSVs. But there are other options, and you'll find those in the ROCm-SME documentation. And so in this particular example, I'm talking about sampling on a single node. We're kind of in the distributed world where we want to run on more than one node, and there's a guide for how you can do that in our documentation if you're interested. So the next I'll talk a bit about Jax, but in case there are any questions related to what I just talked about, do you have questions? Okay. So, what is Jax? And the answer that pops up on you on the Jax documentation is that it's NumPy that run. It's like NumPy, or it is NumPy on the CPU, GPU, and TPU. And it also has great automatic differentiation for high-performance machine learning research. And apparently this automatic differentiation is a big deal. And I need to say, I'm not an AI person. And I also want to show you that, and a good use case is if you want to build an AI model from scratch. Jax might be a good idea. And something that might be a question to ask, is it fast? According to this figure, it's fast. I think that those are machine learning models or something. I have no idea what it's doing, but it's fast comparatively fast to other tools that you might be interested in. So, what do I want to show you today? First, I'll give a short sample on how to install Jax on LUMI-G. I'll highlight some key features of Jax, like its NumPy-like, this automatic differentiation, vectorization, just-in-time compilation, and I'll show you how to parallelize it across a single node with multiple GPUs and across multiple GPUs on multiple nodes. And we'll have a live demo at the end. So The LUMI support team is really helpful. They have provided us with, so someone asked about Docker containers, and the LUMI support team has provided a bunch of container images that can be installed through EasyBuild. And EasyBuild, it's like a tool you can use to install software on clusters. And let's see what we have here. So the Jax image that's available is this one. I understand it's kind of an old Jax version. I wouldn't know, but if you want a newer one, LUMI support team will probably help you get a newer version. We create an EasyBuild config file. We specify which image we want to build on. And this is literally the installation steps. You load the modules you want, and you install it through this EB command. It's very simple. And all of the details, if you want to do this yourself, is available in the documentation linked at the NLDL webpage. And let's say I don't want only Jax, I also want PyTorch or whatever. It's easy to create what's called an overlay image to the container, and you can install PyTorch through that. That's also well described in our documentation. So a bit more on Jax. It's lightweight, NumPy-like array, API for array-based computing. It has these composable function transformations. And I'll show all of these. And it can be executed on the CPU, TPU, or GPU without changing the code. And that's actually something I find a bit scary, that it just works whatever architecture you're on, because you might think you're on a GPU, but you're not. All of the code examples I'll show here are available in my GitHub repo. You can find it through the QR code, and the QR code can be found in the presentation deck. There are also more examples there. Okay. So the first thing I want to show is, first, can I have a show of hand? How many of you use Python? Okay. How many use NumPy? Okay, very good. I was kind of assuming everyone did, but looks like I'm hitting it well. So this is what a convolution might look like as a NumPy implementation. Can someone who has not used Jax before guess how I would write this in Jax? Please? Let's see. I think this guy is clever. And if you look at this, the only real difference is if I wanted, I could have said import jax.numpy as np, and then there would only be one line difference. Here I'm clever and I set JNP, but yeah, it's if you've written NumPy at least once, you're probably able to do it with Jax as well. At least I was able to. So that and let's see what the output looks like, just to be sure that I'm not lying. So I did this test. You see, we have the same input in both X and W, and we get the same result. Great. Another example is automatic differentiation, and I had never heard about it before I heard about Jax, but apparently it's kind of important for people that do machine learning. Is it correct, or maybe not? But it's really easy to do it in Jax. You just use the jax.grad function, and you get a new function called, in this case, gradient grad square. What do I say? Grad square scalar. Yeah. And let's see if it does what you think it does. And we see that square of 2 times x is 6 and x is 3. So it looks correct, right? A problem here is that this function only works on a scalar value. Luckily, the people that implement Jax have thought of this, and we can do something called vectorization. And it's as easy as doing the auto-differentiation. You just use the Jax V-map. And now we can do this same example on not only a scalar, but an array. And this looks more or less correct. I haven't checked each number, so if you want, you can do that for me. And another thing that I think is a big deal, I haven't benchmarked it myself, but they have something called just-in-time compilation, which, if I understand it correctly, the code is pre-compiled before you run it, which can create huge speed-ups. Here we have an example from the Jax documentation, where they have this scaled exponential linear unit, which apparently is a machine learning thing. And if we compare the timings of with and without the just-in-time compilation, we see that the pre-compiled version is about an order of magnitude faster than the non-pre-compiled. And again, the only thing you need to do is use this jax.jit on whatever function you're using. Right. So first I want to show you how, I want to say easy, because it looks, at least there's not many lines of code. And to distribute this, we take the vectorized grad squared, and the only thing we do is use the pmap function. And there we have it. We have something that can be distributed across multiple GPUs. Let's look at this example. So the differences here is that I modified the X input so that it can be distributed across as many nodes or as many GPUs as I want. So let's see if it works. And here we see that we have 8 GPUs. We prepared the data, and the outputs are what you would expect it to be in this case. But we kind of promised you guys that we would do things on more than a single GPU. What I'm trying to show you here, it might look a bit scary, at least if you're not used to MPI. I'm not used to MPI, and I was able to do this. And the reason why I need to use MPI is that Jax is really good at distributing it, but it's not as good at collecting the data in the end. So MPI is only used to gather the data at the end. And the only real difference here is in line 33, where I use the process index to make sure I distribute the data and create the data so it can be distributed across as many GPUs as I want to use. And again, this was the output. This is the output if we are on 8 GPUs on a single node. And if, let's see, we can compare it with the simple distributed example from before. And it should be exactly the same. The difference here is that the first example can only be run on a maximum of 1 node, which for LUMI-G is 8 GPUs. But the second example, you can run it on 2,000, almost 3,000 nodes if you really wanted to. So here I only did it on 1 GPU, but I wanted to try on more than 1 GPU live, just for fun, so you can see at least Something I find really, really cool with LUMI-G is the sheer amount of power you can muster if you want it and you know what to do with it. So I'm not an AI person, so I've never seen a need to use more than use all of this data or all of this power. But I hope this demo can motivate you to see that, okay, I can really train big stuff here. So let's go to the job script. So at the top here, we see the directives we have for our waiter. Sabry talked about. So what we have, we specify the project. This is the project I happen to be on. This should be fast, so I'm reserving 4 minutes. We don't need that much, but why not? I say I want to do this on the standard G partition. I want 8 GPUs per node. I want to reserve the full nodes. And a question I have to ask myself or ask you guys, how many GPUs do I need to run on for it to be kind of cool? Like 8 GPUs, I guess most of you guys have access to that, right? Let's try 64. Yeah, it might not be. So this is live. I don't know if it will work, but let's try 64 GPUs. And so down here, I should also just reference this. This is where I load the modules I want to use, which in this case is Jax. Hicham briefly mentioned the CPU bind, where I tell Slurm where the physical locations of the GPUs are. Because when you really want things to go fast, like physical, we can't move faster than the speed of light. So let's try to have things as close together as possible. Let's see if this works. So I have a video recording if it goes wrong, but let's try. Let's see if it's running. Oh, it's running, so good. So we see we have 8 nodes. These are our nodes. And one node has... Oh, no, it's too late. It's already done. Let's see. Let's just me. Oh, it's not done, but I don't have it in my fingers. I can't type fast enough. There it is. Let's see if it's printed. Cat, and we do distributed auto-diff.out. And here we go. So, not the most interesting data, I guess, but I'm not the AI scientist you guys are, so I challenge you to make it more interesting. And we see here, we ran this computation on 64 GPUs. So that sums up the most important things I wanted to touch on. So thanks for listening.